Hello all, welcome to week 7 of this course, Chemical Engineering, Fluid Dynamics and Heat Transfer. Okay, so next 6 lectures, uh, lecture number 7 to 12 will be heat transfer. So the earlier part was taken by Professor Ravi Brata. Now Professor Arna Bhatta will be covering this part to do with heat transfer. And as I said, I will take an extra class in the 13th session where I will try to cover the turbulence portion or if something more interesting pops up like a combination of fluid dynamics and heat transfer, something like that we'll see. So yeah, basically like in this part we'll be covering conduction, convection, radiation, or the equation of energy that in the differential form. Like we had the Navier-Stokes equation for the fluid momentum transfer. Like that we will have energy transport also. So we'll have different types of differential equation. Then we'll look at steady state conduction as well as unsteady state conduction. We look at concepts like critical radius, extended surface like fins and all. In transient conduction, we'll be looking at the lump system model and some numerical methods also. After that, towards the end of this part of this course, we'll be looking at forced convective transfer and natural convection. We'll also look at boundary layer concepts that arise in heat transfer. And the last class, I think, will be about boiling, condensation, etc. And then, of course, radiation is also there. Okay, so I hope you have all gone through the lectures of this week. Like this was just introduction stuff. Okay, so nothing much to cover at least in this class. Real numerical solving will come from next class, but because Sir just given introduction in this class. Anyway, let us have a look. We'll slowly start and we'll build up the heat transfer concepts also in the next 6 classes. Okay. So just like in momentum transfer, we had this constitutive relation known as Newton's law of viscosity. So in this case, for heat transfer, we have 3 types of transport. One is conduction, one is convection, and one is radiation. And when you talk about conductive transport of energy, we'll have something known as Fourier's law. So that's a constitutive relationship in case of heat transfer. So just write it down. Okay. So the heat transferred Q is minus K del T. This is the del operator, right? Or the gradient given as dou dou x of something I cap plus dou dou y j cap plus dou dou z of k cap. Okay. So Q is like the heat transfer per unit area, also known as heat flux. Yeah, so this is the conduction, this equation it comes from here. This is the heat flux, the heat flow rate divided by the area, unit area. Okay, it's minus k dt by dx. Why the negative sign is there is because the heat flow happens from a place of higher temperature to a place of lower temperature. So if dt, say del T is T1 minus T2, right? T2 minus T1. So it will be minus of T2 minus T1 is equal to T1 minus T2, where T1 is greater than T2. So then the heat flows in that direction. Okay. So yeah, K is the thermal conductivity. So in general, for most of the cases, we'll take K is isotropic. Fine. Isotropic means independent of direction. But K can also be anisotropic in some cases. For instance, in case of wood, so there heat flux is different in different directions because the grains are oriented in one particular direction, and whether you take heat flux in that direction or perpendicular to it, so heat flux will be different. So in case of wood, heat flux is different in different directions. So it's an anisotropic case. Okay. For I'll make some comments. Okay. For anisotropic case, K is a tensor, right? So vector was order one. This is order two tensor. Okay. So K dt by dx will be like this matrix multiplied by this matrix. Okay, so this is 3 cross 3 matrix. So this should be like 3 cross 1. Okay. So basically it will be like this one. A column vector. Okay. But, so in anisotropic case, K is a tensor. But even there, mostly the off diagonal components are zero. Just simplifying our problem. So what is off component? Off diagonal means only the diagonal elements are non-zero. K1, K2, K3. The remaining elements of the matrix are zero. Okay. So you can write Qx as minus K1 dou t by dou x. Qy you can write minus K2 dou t by dou y. Qz you can write minus K3 dou t by dou z. Where delta T, the temperature gradient, is given as dou t by dou x into Ex cap or Ex direction, x cap plus dou t by dou y into Ey plus dou t by dou z into Ez. Okay. So just like we saw in case of the stress or tensor stress vector also in case of momentum transfer. So here also, say there is some surface over here. This is a normal to that surface. And say heat flux is like this. So flux passing through the surface you can write as n dot q. It will be a scalar only. Q dot n. Okay, so can any of you see? Nobody's here, but still, what is the unit of flux of heat? Flux of heat is joule, the unit of energy, divided by unit area divided by unit time. So flux is what? Basically transfer of any component say z divided by area and time. Fine. For instance, in case you have momentum transfer, momentum flux will be what? Momentum kg meter per second, mass into velocity, divided by area divided by time. It will be kg per meter second square. Okay, I will give you a small problem. Say there are two walls like this. This is at x is equal to 0. This is at x is equal to 1. Forget about units. Just take the absolute values. And I'm saying that the thermal conductivity K is equal to 1. This wall is at 300 Kelvin. This wall is at 500 Kelvin. Okay. There is some temperature profile in between. It's not a linear line, okay? Say something like this. This temperature profile is given as 300 plus 200x square. So we have noted down this problem. So the question here is calculate heat flux at the two walls, left and right boundary. Okay. And we know that what is Q, Qx will be minus K dt by dx. So just take a couple of minutes and try to solve it. Very easy. Just apply this formula, plug in the value of T from here with the given problem. And at x is equal to 1, what is the heat flux? At x is equal to 0, what is the heat flux? Just find out. So I hope you guys found out this answer. So in this case, as k is equal to 1, qx is just minus 1 into dt by dx. So just minus dt by dx. And what is t? T is 300 plus 200x square. So what is dt by dx? 400x. So qx is equal to minus 400x minus dt by dx. So at the two walls, that is at x is equal to 0 and x is equal to 1, they correspond to, at x is equal to 0, it is just minus 400 into 0 is equal to 0. At x is equal to 1, it is minus 400. But as you see, like, this is a very non-linear profile, 300 plus 200x square. So if you see there is a heat flux term in the left hand side, but not in the right hand side. So it is not a very realistic case, right? Unless there is a source term in the middle. In between the two boundaries, there has to be some source term that can only explain this discrepancy between the heat flux and this end, and also the nonlinear profile. So no heat generation means T should be linear. Okay. So another thing is that for energy transport, we generally look at enthalpy term because enthalpy is a good representation of energy in chemical engineering. Okay. So the Fourier's law, for instance, in the y direction, the heat flux Qy we can take as minus k dou T by dou y. So let us divide and multiply by rho Cp. So it's minus k by rho Cp into dou by dou y of rho Cpt. And if you're familiar with chemical engineering thermodynamics, this rho Cpt is just the energy term. Okay, so it's minus k by rho Cp into dou by dou y into the enthalpy. And k by rho Cp is alpha. If you remember the dimensionless number, I'll come to that now. Okay, first I just make some notes. So in general, rho and Cp are constant, independent of position. Okay, and enthalpy by volume, like mass by volume is density. So it's a concentration of mass in the system. So enthalpy by volume is the energy concentration. Hmm. So over here, the Fourier's constitutive relation, we saw Qy is equal to minus k by rho Cp into dou by dou y of rho Cpt. So this k by rho Cp term is what is known as thermal diffusivity. And I'll represent it by alpha. So it's thermal diffusivity. Like we have mass diffusivity, we have momentum diffusivity. Similar to that, the analog in heat transfer is thermal diffusivity. So the momentum diffusivity is mu by rho or kinematic viscosity. And in species diffusion, we have like DAB. So you'll notice a similarity between these different types of diffusivities. So can you just find the units of this alpha? Just take a couple of minutes and try to find the units of this alpha. The units of density is quite easy. It's kg per meter cube. Find the unit of K and find the unit of Cp. And from there you will get the unit of alpha. Okay, so I'll just you solve, I'll also solve, and we'll see whether we get the same answer. So from Fourier's law, Q is equal to minus K dt by dx, where Q is the heat flux, that is the rate of energy per unit area. So that unit will be watt per meter square, right? Units of K we don't know. dt by dx means T is unit Kelvin, X is unit meter. So meter meter gets cancelled, and K's units you will have watt per meter Kelvin. Okay, so what is rho CPT? I told it is the unit of energy per volume. So what will be the unit of rho Cp? It will be joule per meter cube Kelvin. Understood? So K by rho Cp, what will the unit be? K's unit is watt per meter Kelvin. It's watt per meter Kelvin. Rho Cp's units is joule per meter cube Kelvin. So meter cube Kelvin will go to the numerator. So it will be watt meter square by joule. And what is this joule by second? So joule by second into meter square by joule. Joule gets cancelled. And we have meter square by second. So now if you remember the kinematic viscosity that we went through in momentum transport, nu, that also had units of meter square by second. Though we are not covering it here, in species diffusion, there is something called diffusivity, say between two species A and B, DAB. So that unit is also meter square by second. So we find an analog between the momentum transport, the heat transport, and the species transport in terms of diffusivity. Each of them has a corresponding diffusivity. It is kinematic viscosity in case of momentum transport. It is thermal diffusivity in case of heat transport. And like that, similarly, there will be a binary diffusivity term in case of species transport. So alpha, nu, and DAB having units of meter square by second. Yeah, this DAB is the in mass transfer. You must have come across this term. It's the binary diffusivity. Okay, I'll also note down some dimensionless numbers over here. Though strictly not part of this curriculum, I think you should know, as chemical engineers, you should know these dimensionless numbers, named after some very famous scientists. For instance, Prandtl number is mu by alpha. Okay, the momentum diffusivity by the thermal diffusivity. The Schmidt number given by SC is nu by DAB. Like that, there is something called Lewis number. That is alpha by DAB. So it's just the ratio of the different diffusivities. This is just extra information. You won't be asked all this in the quiz, but since we are covering diffusivity, I just thought I'll give these uh, different dimensionless numbers which use the diffusivity concept. So some other extra points about this are, in case of gases, generally it's experimentally observed that the various diffusivity, momentum diffusivity, mass diffusivity, heat diffusivity, those magnitudes are almost same. Okay. So in case of gases, the Prandtl number, Schmidt number, Lewis number, they're almost one. For common liquids, nu is greater than alpha, is much greater than diffusivity. Because species diffusivity in liquids is quite less. In gases, it's more. But in liquids, since the particles are so closely packed together, it isn't very easy to diffuse. So the DAB in case of liquids is quite low. So Prandtl number in case of uh, gases, I already said that uh, Prandtl number, Schmidt number, Lewis number, etc. in case of gases are close to 1. So Prandtl in case of gases number is equal to 1. But in case of liquid, it can be up to 10. In case of water, organic liquids, etc. Basically, most common, this one, this category. The Prandtl is close to 10. In case of oils, it is much greater than 1. Right? The thermal diffusivity in oils is much less, and the momentum diffusivity is quite high. So it's much greater than 1. And in case of liquid metals, it is much less than 1. Because in case of gas, if you see over here, say compartment and dry control volume, you'll have many particles in the liquid, but much fewer particles in this control volume in the gas. Because the particles are more spread out, not very close to each other. So this is case of gas, this is case of liquid. So basically, when you're going from gas to liquid, typically the viscosity increases about 100 times. It's much more easier to make it flow, much more difficult to make it flow. The thermal conductivity also increases because the particles are close to each other and so more conduction can happen. But the increase is not so drastic. It increases about 10 times. And any idea what happens to the diffusivity as you go from gas to the liquid? It obviously decreases, okay? Because the particles are much more spread out now, not so easy to diffuse. So, but the order of magnitude is 10 to the power 4. As you go from gas to liquid, the binary diffusivity, for instance, can go up to 10,000 times lower. Fine. So, what is a typical energy equation? I'm not going to, maybe in the coming classes, we'll go into more depth. But as I said, that rho CPT, it gives you an indication of enthalpy per unit volume. Okay. So, our energy equation is roughly of the form. The unsteady term is dou T of rho CPT. Then there is a convective term, divergence of rho CPT V. It's a convective term. The diffusive term is just minus del dot Q. Again, where Q can be given by the Fourier's law. And there is a heat generation term, say HV. Okay. So this is a general typical form of a energy equation. Q is given as minus K del T. That comes from the constitutive relation known as Fourier's law. So now if we simplify this, let's also, since rho Cp are constant, let's take them out of this divergence operator. So basically this form of equation will get as rho Cp dou T by dou T plus rho Cp comes out. So it's just del dot Tv is equal to K del square T because Q is equal to minus K del T. And obviously the HV term will remain as it is. So this del square T, like this is known as the Laplacian operator. Del square is basically del dot del. Maths it's known as Laplacian operator. Like in Cartesian coordinates, del square will be dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Okay. Okay, this t also you can take out. I forgot to take it out. Because t is like anyway, unless like, yeah, maybe let it be in because t can also be a function of space. Suppose we can take t out here. So rho Cp v dot, like, what we'll do is that the rho Cp del dot Tv, let us break into two parts. It's rho Cp v dot del T plus rho Cp T del dot V. And what is del dot V? If you remember, it is equal to 0 in case of incompressible flow or incompressible fluid. So once this incompressibility comes into the picture, del dot V is equal to 0 and we are left with just this term. Fine. And this term, when you add with the unsteady term, you can take rho Cp common. So it will be rho Cp into dou T by dou T plus V dot del T. This is nothing but the substantial derivative, if you remember, right? It's rho Cp capital dt by dt. Okay. So our equation becomes rho Cp capital dt by dt. 1 second, I will call. Hello, sir. Okay, so it's just substantial derivative rho Cp capital dt by dt. Right hand side is k del square t plus hv. So using this formula and appropriate boundary conditions, we'll solve a couple of problems maybe in the next class. So for now, just note it down. Now let us divide both left hand side and right hand side by rho Cp. So it's capital dt by dt is equal to K by rho Cp into del square T plus HV by rho Cp. Okay, so this K by rho Cp is what? Alpha, thermal diffusivity. So capital dT by dt is equal to alpha del square T plus HV by rho Cp. So the underlying assumptions in this equation are that it's a pure fluid. It has uniform properties, constant properties like density, Cp, etc. And there are negligible viscous dissipation. Viscous dissipation maybe will come later in next class or something when Sir discusses the energy equation in its totality. So negligible viscous dissipation and pressure variations. These are the underlying assumptions for this energy equation. So let's take a 5 minutes break now, and then we'll come back and look at the boundary conditions. Like in case of momentum transfer, also we had some boundary conditions, right? So here also we'll have some boundary conditions. So just take a break, small break. Final part of today's class. Let's finish with the boundary conditions. Basically, there are three types of boundary conditions similar to the ones we saw in momentum exchange. Okay, so there are some underlying assumptions over here. No interface with heat source. There is some interface separating the two media, right? So there is no heat source in that particular interface. Also, no bulk flow across the interface. So suppose there is an interface over here separating medium B from medium A. What this one says is that the diffusive flux normal to the interface is continuous across the interface. So I'll just put it in words now. Diffusive flux normal to the interface. Continuous across the interface. Okay. So Q and A is equal to Q and B. If some heat source were present, it would have been Q and B is equal to Q and A plus something. So, or Q and B minus Q and A is equal to BS, where BS is the heat source. Second boundary condition is a global thermal equilibrium. This phase A, this is phase B. See, there are 3 points here, one, two, three. Just give me 1 second. Sorry for the noise. Okay, so there are 3 points, one, two, three. So this is medium A, this is medium B. So this is TB1, TE1, TB2, Ta2, Tb3, Ta3. So the global thermal equilibrium says that across this interface, Ta1 is equal to Tb1, Ta2 is equal to Tb2, Ta3 is equal to Tb3. Okay. So this does not say that Ta1 is equal to Ta2 equal to Ta3 or Ta1 is equal to TB2 or something. It just says Ta1 is equal to TB1, Ta2 is equal to TB2, Ta3 is equal to TB3. So it does not mean this. Fine. So assuming that, say this is a wall, there is some solid here. This is the solid liquid interface, and this is the fluid. This is the x direction. So say this is x is equal to 0, this is x is equal to L. So from the first two boundary conditions, we see that our temperature profile will be something like this, and minus K1 dt1 by dx is equal to minus K2 dt2 by dx at x is equal to L. So this is at x is equal to L, the interface between the solid and the fluid. K1 is the thermal conductivity for the solid, K2 for the fluid. Fine. And also T1 is equal to T2 at x is equal to L. So this is the global thermal equilibrium. Pardon me for the noise. It's a lab now, so generally take the class from home, but there's always some noise in the lab because of people working. The third one is the convective boundary condition. Okay, so for instance, this applies whenever there is flow. See, these are solid walls, okay, and there is some fluid flowing into this. Say this is some channel, solid on either side and fluid flowing. So this is the case of confined flow, or it can also be like this: a solid ball and fluid flowing across it. This is a case of unconfined flow. So TB, say the fluid's temperature, it can be the cup mix temperature or the bulk temperature. Bulk is generally given as T infinity, cup mix is given as TB. So maybe in the coming classes we'll look at the differences between these two. Thermal plus assume that it's the temperature of the fluid outside. So this convective boundary condition is K minus K dT by dx at 1 is equal to H into T1 minus T. Okay, H is the heat transfer coefficient. H you will get from then something called Nusselt's number, which is a function of Reynolds number and Prandtl number. There are some correlations. We'll look at all that in the coming classes. Just know that this is one type of boundary condition. Minus k dt by dx is equal to h into T1 minus Tb. That is a net heat flow because of conduction is balanced by the heat transported out by the fluid because of convection. Okay, so we'll call it a wrap with this. Not much was done in this class. So I just thought we'll have a nice introduction. Next class, like we'll delve deeper into this energy conservation equations and we'll apply the boundary conditions and solve some problems. Okay, thank you.